So building a basic search app is not that hard. And you can get, I'd say there's a lot of tuning that comes with Elasticsearch and getting the behavior and the relevance, notion of relevance just right. But getting the thing out of the box and turning it on, it'll actually get you about 50% of the way there. So it's a real quick technology to get up and running and get some good results. In order to install and run Elasticsearch, this is pretty easy. You all probably know what wget is. So you can pull down find your favorite mirror, pull down Elasticsearch. In this case, I do need to update my notes here. It's a little bit older version of Elasticsearch. But pull it down, unzip it to wherever you want it to live, cd into that directory, and then start the binary, bin/Elasticsearch. Once you do that, you can just curl localhost at the Elasticsearch port 9200, and it tells you, hey, for search, like in case you forgot that it was for search. But Elasticsearch is now up and running. And just like with MySQL, with Elasticsearch, you will want to think in advance about the type of data that you're going to be interacting with and build a schema for it, or as they say in Elasticsearch, a mapping. Now, Elasticsearch is interesting here because early on they advertised that they were a schemaless data store. In the age where MongoDB was rocketing off, everyone was kind of tacking onto this. And it was true to an extent that you could just start dumping information into Elasticsearch. And that's gained Elasticsearch a lot of popularity, but it's still kind of an anti-pattern. So in my opinion, over years using this technology, it's still very important to think through what you're getting ready to do with this thing. So setting up the mapping is simple. Everything in Elasticsearch is a JSON interface. And in this particular, this is a Python conference. So every example that you'll see here, I am using the Python client. But it's really nice. It's really a fairly thin layer over the JSON interface of Elasticsearch. So when you're setting up a schema, all you have to do is specify the fields that you're going to have. In this case, ID, name, description, city, start date, price. And you get all of the things that you would typically think of existing in a data store. So you have numbers, integers, floats, strings, dates. It's actually, so you can start to get more complex things like dates. You can get locations that are a little bit more aware than just two numbers. It knows what a location is. But one thing I'll be focusing on is not only can you have strings, but you can say that your strings are special in some way. For example, an ID is a type of string, but it is a string that is not analyzed. That means that we're not going to do any special massaging and trying to understand this as in a string from natural language. However, both the name and the description here I've marked as having an analyzer that is English. So this is me giving Elasticsearch a hint that not only is this blob of bytes actually text, but it's text of English. And I'll show you what that means to Elasticsearch in a little bit, but it's interesting because you don't have to put English here. You can put Chinese or Japanese or any language, most any language that you'd want, and you can make up your own stuff. So there's interesting things that you can, extra rules you can put in for, like if you have camel case strings because you're indexing programming languages, you can break that up and make your own analysis chain for it. And then, of course, here's me using the client. You create Eventbrite with that mapping structure. Okay, so we have an index set up, ready to receive events. Actually adding the events at that point is pretty simple. You have an array of events, and it's just JSON blobs again. The client is nice because you can use date times, and it does the right thing. And then the simplest version is for just an iterator. For every doc that you have, then dump it into Elasticsearch. This does make an HTTP request for every doc, so there are batch methods once you actually really want to put this into production. That's an easy way to get up and running. Okay, so now we've got a bunch of documents in the index. The next bit is to pull stuff out of it. And the easiest way to explain this Oh yeah, sorry for the microscopic text. How horrible is that to the people in the back? I'll just speak louder. Um, so the simplest building block for pulling stuff back is this match all query, and it does exactly what you think. It's effectively the select star from the events table. It gets everything back in the order that you indexed it in, and you don't have to understand what is on the screen here, but I'll provide these notes on my Twitter account later. You can see it, but it gives you back what you'd expect. It tells you how much time the query took. It tells you if there's any errors, and obviously, importantly, it gives you all the hits back, all the documents that match the query, sorted by how well they match the query. In the case of match all, there's no notion of relevance, so you just get them back in the order that you index them. All right, so that was like the hello world of making a query, but there's a lot of different things you can do to craft the notion of relevance. What is an important document? What should match? What should not? And the smallest building block for these is the so-called term query. So if we have an index document, it's an event in Nashville. If I wanted to make a filter over all the documents and only hit documents corresponding to the city Nashville, then that's a term query. I say this is term, the field is city, the token is Nashville. The special thing about a term query is, just like earlier where I said not analyzed, term means that this is just a token. It has to be capital Nashville. Doesn't do anything special. And so that's a match. But where it gets interesting and where you really get a benefit from a search engine is when you start incorporating this notion of, hey, this is not just a string, this is actually English text. And so if we have a sort of stupid document here, name equals Filbert sorting for fun and profit, then a query that is not of type term, but of type match, actually applies that special knowledge about this is English. And so rather than looking for sort Filbert the exact tokens there, it knows that it can be lowercase. We can split on spaces. Sorting and sort should be basically the same information. And so that's a match. So compared to what you think about how you'd have to do that in MySQL, you would have to make a horrendous query to make that one simple match right there. And it would also be very poor performing for reasons that I'll get into in a little bit. Getting more and more complicated because your application has to have a lot of different ideas mixed together. You can do phrase matching. So not only do we have the notion of matching documents that have these terms, but we want a document that has the term sorting and Filbert in it in that order. This is not a match because the original document had Filbert sorting. However, if we search for Filbert's space sort, that is a match despite the fact that it's different from the original document. The original document has uppercase and has different parts of speech. But think about as a user looking for something, you don't quite remember the name of the movie, but you're probably going to get something like this. So getting these type of fuzzy matches is a specialty of search technology. Filbert fun won't match because there's space between Filbert and fun. Just more example of how match phrase works. But you can add this notion of slop, and everyone chuckles when I do that one. That's what it's called. You can add slop, and it'll find any document that has these two words within a space of two. And you can go nuts with this. I once had a gig with a U.S. Patent Office, and their search technology that they were getting rid of and moving to a different search than ElasticSearch, Solar, they really wanted to know, I want to find this word within the same sentence as some other word, and I want to find it before or within like some number of words. And so you can take this same behavior and overload it and get some really complex search behavior. But everything I've showed you to this point is just like atomic. It's like I want this thing or that thing. You have to have a way of gluing these things together. In ElasticSearch, that is a Boolean query. In normal notions of Boolean queries, in normal notions of Boolean, you think ands and ors and nots. Elasticsearch has that, but using different terminology. Rather than ands, we say must. Rather than should, or, we say should. And then not is must not, so that one makes pretty good sense. But the idea, and if you play around with a few queries, you see why they moved to this terminology. Usually you have an array of things that must match. So in your Elasticsearch query, you have a must key, and so you stick everything that must, all these subclauses that must match there. And additionally, you have several things that don't have to match, but should match. If they could match, if you could find documents that also happen to have these other things, it should boost a little bit higher. So that's yet another array of things that if it matches, then you get a better score. Each one of these pieces, you have the ability to also adjust weights. So we're starting to get into a notion of how search understands what's important to your customers and to your business. You can not only match documents that match their queries, but you can also boost documents that we need to sell quickly because they're expiring inventory or something like that. And that leads us to our next big topic, search relevance. I'm curious, how many people here have heard of the notion of TF-IDF? Okay, only this half of the room. That's interesting. You guys should have mixed in a little bit more. It's not a hard concept, and so I think it's intimidating at first, but I can break it down pretty easily. This will be a little bit of a mathy slide, but not too bad. First off, TF is really just means term frequency, and I'll get into that. And IDF means inverse document frequency. And the best way, rather than giving you the Webster's definition, the best way of explaining this is through an example. And let's say a user comes to your website and makes a search for the diddle. Now that seems odd until you realize that one of the matching documents in your index is hey diddle diddle the cat in the field. That's actually a pretty good match for it. So let's do a little practice round and see what this document would be scored as from the search engine's perspective. Term frequency is simply the number of times a term occurs in a document. So the TF for the in this case is 2. There's the occurrence of the is twice. Similarly, just by coincidence, diddle also occurs twice. So TF for both of those guys is 2. So far so good? Good. Inverse document frequency. Sometimes I just wish they'd called it document frequency and just put a 1 over it. It's basically how many number of times the document frequency is how many number of times the term occurs not in this document but across the entire set of documents. So document frequency for the, pretty high. So the inverse document for the is just about 0. Makes sense? And the document frequency for diddle, not a very common word, it only occurs in 7 documents. So it's actually very important, and it gets an inverse document score of 1 over 7, which is a lot higher than 0. So when you finally are figuring out the total score of this document against this query, you put all those pieces together. The score is the TF-IDF score for the plus the TF-IDF score for diddle. And you probably makes sense, but just be a little bit redundant. TF of the is 2, IDF of the is 0, goes away. TF of diddle is 1/7, or is 2, and IDF is 2/7, and so you get the final result of 0.2857, blah, 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 blah. But the idea is every document is going to go through the same process and be sorted, and so the way that you craft your query informs the way that this math works in the documents that, you have 10,000 matches, but you want to make sure you do the right thing so the top 10 search results are what they want. Okay, yep, so that was a pretty overloading slide. I always like to take a break after heavy slides like that, and I think clay work is really therapeutic. And in particular, I think that this is my favorite one. That's great. We're gonna watch that one more time. I love this part of this talk. Okay. Service is a good break. So to this point, how much time have I got left, by the way? So at this point, we've done a lot to get you in the mind space of how search works from a mechanical perspective, how to dump stuff in, how to pull stuff out, what it can do as compared to other data stores like MySQL that I was picking on. The next thing that we want to do is dive inside the data store and give you a little of intuition about how the pieces inside work. And what you'll find is it's not that complicated. So after this section, you'll have a little better understanding about when it's right to use ElasticSearch and when it's not. So getting data in any data store, there's two main chunks that you have to understand: how you get data in and how you get data out. So that's the outline for the next bit. The first step of getting data into Elasticsearch is a step called analysis. And basically, we're going to take a document, and in this case, I've got just one field out of a document, and I will show you how it effectively gets shredded and rearranged and shoved into the data structures that make search technology so fast. Our example in this case is the sentence, "The conspirators conspire conspicuously." I chose it so that I could almost not pronounce it at a conference. Tokenization, that's the first step. In this case, we have told Elasticsearch, hey, this is English, and that gives us some interesting things that we can play off of. We know that English is split on white space and also punctuation. We can basically throw out punctuation. An interesting side note that I always like to make here is this is not true of a lot of languages on the other half of the earth, right? So like my wife is Japanese, and so there are places where you could have symbols right next to each other and they're different words, and the same thing, doing the same thing in Japanese, which you still have to do, you have to have a really complex algorithm to know where the best place is to split these things to make a logical sentence. So tokenization itself is a fairly deep topic. Next step is actually a fairly shallow topic, lowercasing. Pretty easy, but if you have someone type in lowercase, you better make sure that it matches a document that has uppercase letters. Stop wording. A lot of the words in English are just noise words. They help us understand where things are placed relative to each other, but they don't really change the content. So we can throw away words like the and is and was and stuff like that. And perhaps my favorite step of analysis is stemming. This is another place where, because we've given Elasticsearch the hint that this is English, it knows some interesting tricks to do. If you want a document for farming to match a query for farms, which is often the case, then effectively what stemming accomplishes that. You can take a word and using a statistical technique, you can effectively chop off and sometimes modify the end of these words to make tokens that are easier to match no matter what the intent was of the people searching. All right, the next step after analysis is indexing. So our example sentence has turned into these three tokens: conspire, conspire, conspicu. Sounds like Latin. Let's say that this is document 1. The secret sauce of Elasticsearch for being so fast is effectively during the indexing process, it takes these sentences, turns it into a bunch of tokens, and then it effectively transposes that. So instead of document 1 has these tokens, at the end of the analysis, when you've gone through all of your documents, you say these tokens have these documents. So document 1 had these tokens, but in the end, conspire appeared in document 1 as well as these 2 other documents. Conspicu appeared in document 1 as well as these 3 other documents. And so effectively, from a Python point of view, you could implement this with a dictionary where the keys are tokens and the values are an array of IDs. Now, this under the hood, this is actually implemented in Java, and they do a lot of sneaky stuff. They shim extra information in the keys, so all the notions of document frequency, which we use for scoring, get shoved over into the keys when you look stuff up. And all the notion of term frequency, that's the other half of the TF-IDF, are basically hidden into the values on the right, as well as other information like the positions of the words in the document, so you can do phrase matches and stuff like that. But effectively, a simple search engine is just a Python dictionary like that. All right, so we have now gotten all the information into the index. The next half of the equation is getting information out of the index. So our inverted index looks like this. And make this interactive. Given that data structure, what's the easiest way to find all documents that contain conspicuous and aardvarks? Anyone? Yep, that's all you have to do. Effectively, you have, these are lists, but they might as well be sets or iterators, and you find whichever one IDs occur in both. And you can build arbitrarily complex things on the same idea, or it's just a set union. And if you combine a more complicated search, it's a set union followed by a different set or set intersection. Pretty easy. So, but that's only half the puzzle, because MySQL is really good at finding documents that match. I just showed you how Elasticsearch finds documents that match efficiently. But Elasticsearch has to turn around and do a sorting algorithm that is part of the important aspect of search. When Google gives you back the 60,000 results it supposedly says you have for your query, you only see the top 10, and they're usually pretty good. If you scroll down 50,000 pages, they would probably be less good. So it's important to know how that works. Effectively, what happens is when your user gives you a query, you have an iterator of all the documents that match. And so what you do to find the top 10 is you initialize, you have a priority queue. Do you all know roughly what a priority queue is? Okay, we can talk about that. But effectively what you do is every document that comes through, you take it off of that iterator, you look at all the other secret stuff we've hidden in there and find the score for that document, and now you put the document and that score on your priority queue, and there's something there that's just iterating, doing that with every single match that exists. The interesting aspect of this priority queue, though, is that it doesn't keep up with every document it ever sees. It's only of length 10, or whatever you tell it to be. So as soon as you get past, the top 10 documents, you've got one that's scores lower than the documents, then it compares itself to not even 10, like, it's order log in or whatever. It compares it to a few of the documents and says, I'm lower than all of these, never think of me again. And so the action is actually pretty efficient. Now there's a little side note. This is another intuition that might be important for Elasticsearch. If you're doing some sort of relevance, but you also want to return 100% of the documents, think about how you'd implement that. If I want to, deep paging is what this is called. If you've got a robot scanning your website for the 10,000th to 10,010th most fun event, then this means that you have to have a priority queue that is 10,010 long, and you sort all the documents in, throw away the first 10,000 of them, and give that chunk back. And guess what happens when the robot goes to the next page carelessly? It just gets worse and worse and worse. So that's one important intuition to think about search technology. Elasticsearch allows you to turn that off. So if you don't care about relevance, but if you do, I would recommend not letting anyone get past about 500 results. All right, and then I already said it returns the most high priority contents from that queue.
You have a priority queue for the top 10, and anything that falls out of that just goes into a bucket, and who gives a crap what works the rest of the
That's effectively what we do. Like after top 10, they go away. The data structure is only 10 items long, so it can't hold any more than that. Oh yeah. That's not a bad idea. If I don't know how I would implement that in Elasticsearch. I don't think they make that easy for you. But yeah, that totally checks out. All right. Okay, so I need a little transition slide here, but effectively that gets us through everything that a search engine has been until about 3 years ago. But so search came out of information retrieval, library technology type stuff, finding whatever I wanted to find. But Elasticsearch has started to prove the point really strongly that the same data structures that serve search results are actually really good for online analysis, log parsing, stuff like that. And a big chunk of that is its ability to do aggregations. And I think I can convince you that it's basically what we're doing before, just one extra step, and you get this nice ability to do aggregations for free, almost. So just like before, whenever we're aggregating over the, we want to find a histogram of the ticket prices or something like that. We have all the results that we had from before. We do the sorting like we did with them before, but while we still got that document in hand, we push it through an aggregator. It's basically just a little in-memory thing that says, okay, how many documents have I seen in, from $10 to $20, and it just increments those counters. For every document, it does this, and at the end of it, you pass back this aggregator thing, and you have these really nice results. And it was just something that you did almost as a byproduct of the actual search itself. So with the building blocks that I've given you right now, you can see how we have the ability to easily filter. That's just what a search is. You can group stuff because you can see as the documents are coming through, you can already figure out which group it belongs to. And within each group, you can do calculations to do running averages or anything like that. So to give you a little more intuition about how you might use aggregation, here is how I encountered it for the first time. Let's say you go to Amazon. You're chuckling. Have you seen my? That top book, by the way, is a really excellent book. Like this. So anyways, if you go to e-commerce sites, you see a lot of the original use for aggregations. They were called facets, faceted search. You have a list of subcategories on the side. You have the counts for how many things are in that category. You can click on it, and it serves as a filter. It gives you a little bit of what I call relevance feedback, so you can understand what's actually happening. But people have taken the same data structure, you turn it on its side, and you've got really nice histograms, which at Eventbrite, we're making them prettier now, but you can use them to feedback good information about how many tickets are sold from a particular class. You can take exactly the same information, but a different data set, and give spark charts for how many tickets were sold in a particular day. And you could take, again, counts over buckets, and you can plot it on a map, and you've got a really nice geo information console just to give you intuition about where things are happening in geospatial relationship. And finally, I don't know exactly how to make a picture for it, but analytics, log analytics in particular, are great with ElasticSearch. Building ElasticSearch, building aggregations in ElasticSearch is easy. I'm going to kind of fly through this so I have a couple questions. But effectively, all you have to do is you have your normal query. You keep asking your query like normal, but you add a new section to your query to Elasticsearch called ags. And in this particular case, it's going to be hard to read, so I'll blur over it. But you can say things like, my aggregations, I want you to do counts for counts grouped by city. So that's a term aggregation where the field is city. And I also want you to do a histogram aggregation for the prices with an interval of 10. So that's the second thing. The results come back, and you have the normal search results at the very top, but you have a new section that has these aggregations in it. In this case, I've got the city bucket right there with my Nashville and Dallas and BFE events, and I've got my price buckets for what distribution of events occurred. But a neat thing that you can do, so right now, I really needed a graphic for this. Right now I've got two separate aggregations. A neat thing for us to provide back to our users is not only the histogram of all the events, but we could do a histogram per each city. And you can do this with Elasticsearch. Aggregations can be arbitrarily nested. There's performance issues after some point. But I can say at the top level, do a terms aggregation, so we bucket everything by city, and I get the counts back. And then within that aggregation, do a histogram so that we can show our users, here's the price distribution within the city that you're interested in. The results come back. Very similar structure, except it's appropriately nested, so that for each city bucket, you have the count, and within that, you have sub-buckets for the histogram, so that you can draw it on the screen. That's effectively it. I've been doing this a while, so I have a lot of things to learn, but a lot of other things that I would enjoy talking about. Also, if you're interested in learning more on your own, I know of some reading material. And find me on Twitter. Tell me what I did right and what I did wrong.